Welcome everyone. My name is Mattia Veroni, and in this video I'm going to talk about a practical isogeny-based key exchange protocol with optimal tightness, which is a joint work with Kock and Kristian Gjøsteen. Let's start with the motivations behind our work. The cryptographic community usually puts a lot of effort in building new and more efficient cryptographic protocols. And if you ask the people who care about provable security, they will tell you that the same amount of effort should be spent in designing good security proofs. In a security proof, we take an allegedly hard problem and we use it to bound advantage of an adversary in breaking a scheme. Once we have a security proof, then we can decide the parameters of the scheme in a theoretically sound way. For classical cryptographic protocols, we typically have many security proofs, so that if we fix a security level and we fix a protocol, two different security proofs will result in two different parameter sets. If we have a look at the post-quantum world, then several schemes actually lack a security proof. And in these cases, the authors analyze the existing attacks that can be mounted against the scheme and decide the parameters in such a way that the scheme itself can survive them. But then the research question came up. Can we get a tight quantum-safe key exchange protocol? Spoiler alert, the answer is no. But we can still obtain a slightly weaker result. A security proof consists of two elements: a security model and a security reduction. In the security model, we describe the environment in which our protocol is run, we describe an adversary and its capabilities, and we define our security goals. When building a reduction, we start from an allegedly hard problem. We suppose that there exists an adversary A against our protocol, and then we use A inside of an algorithm B to solve the hard problem. The quality of a reduction can be quantified by its tightness loss L, which appears in a formula here below. This quantity measures how much the reduction loses in terms of running time and efficiency with respect to the original adversary A. If L is constant, then we talk about tight reductions. If L is not constant, but we cannot do anything better than this, then we talk about optimal tightness. We focus our attention on key exchange protocols, which allow Alice and Bob to agree on a shared secret key while communicating over an unsecured and public channel. An extra goal is authentication. After running the protocol and agreeing on a key, Alice must be persuaded of her intended peer's identity, and so does Bob. Authentication can be achieved either implicitly, when it comes for free by the design of the protocol itself, or explicitly, through the use of extra mechanisms such as key encapsulation, message authentication, or signatures. But the use of extra mechanisms typically results in a larger number of exchanged messages, more computations, and the introduction of further hardness assumptions. And for this reason, we decide not to go for explicit authentication and to stick with the implicit authentication. Now, it's impossible to provide in 20 minutes the background necessary to understand the algebraic setting of our protocol. What I want to do instead is to teach you these magic words. The ideal class group of an imaginary quadratic order O acts freely and commutatively via isogenies on the set of elliptic curves with endomorphism ring isomorphic to O. So the magic is unraveled in the paper, in which we spend a whole section in explaining the meaning of this sentence and its application. For now, let me try to explain it through an analogy. So take the well-known Diffie-Hellman protocol of elliptic curves, and let's see how to achieve its post-quantum translation called Seaside by Kock and others, which appeared in 2018 at AsiaCrypt. So on one side we have a set of points of an elliptic curve which form a cyclic group of prime order. On the other side we have a set of elliptic curves defined over Fp and arranged in a graph whose edges are isogenies. The operation on the left is scalar multiplication, while on the right we have an action of ideal classes, which is represented via an isogeny. The one-wayness on the left is guaranteed by the elliptic curve discrete logarithm problem, when on the right we have the key recovery problem, which boils down to finding an isogeny between two given elliptic curves. The protocol is secured by the elliptic curve Diffie-Hellman problem on the left and by the computational seaside problem on the right. So our idea was to use these magic words and to take protocol pi by Cohn, Gordon and others from Crypto 19 and turn it into a post-quantum protocol, which we call pi-side. The good features of protocol pi is that it has optimal tightness, which we can prove it's preserved in the post-quantum setting, and it's quite easy to understand because it's designed over the classical Diffie-Hellman setting. The result is the following. Let's focus on Alice's side. The long-term secret key is A, which is an element of the ideal class group. The long-term public key is the Montgomery coefficient of EA, which is the result of the action of A on the elliptic curve E0, which is fixed for everyone. Now, whenever Alice wants to initiate a session, she samples another element from the ideal class group, she computes the corresponding Montgomery coefficient, and she sends it over to Bob. Bob replies with another Montgomery coefficient, which is obtained in a similar way, and then they both compute the shared key through the hash of this whole lot of terms. Now, this is not just crypto hygiene, which prevents some silly mistakes from the two users, but every term is actually necessary to have the security proof run smoothly, and for example, to deal with long-term key reveals. So, the protocol itself is an easy adaptation of protocol pi. What's not so straightforward is the adaptation of the security proof. Let's start by defining the environment. Over an unauthenticated network, we have mu parties and a central authority. When a party joins the network, it sends the public key to the central authority, which does not require any proof of knowledge over the corresponding secret key. Each party is represented by k oracles, one for each session it can participate to, and each oracle maintains an internal state, which consists of the identity of the partner for the session, the status of acceptance of the shared key, the value of the shared key, the set of sent and received messages during the session, and the role of the oracle, which can either be initiator or responder. So we can define two partner oracles. So an oracle must be the intended partner of the other, or intended peer of the other. They must have complementary roles, so one must be initiator and one must be responder. They must have matching conversations, and they both have to have accepted the key. After the environment and the security goals, which are key exchange and authentication, we are now to define the adversary and its capabilities. In this model, the adversary has full control over the network and it interacts with the oracles through queries. It can register the long-term public key for a new user, which is immediately regarded as corrupted and its public key is anyway distributed to all other users. It can activate the oracle of any user, either as an initiator or a responder. It can reveal the long-term secret key of any user in the network. This user is then regarded as corrupted, and all its oracles will output nothing at later queries. It can reveal the session key, which is stored in the internal state of any oracle, and the target oracle is then said to be revealed. And it can test any oracle, which outputs nothing if it hasn't accepted any session key yet, or it outputs a key, which can be either the real one or a random one. In fact, we are working in the real or random model. So at the very beginning of the key exchange experiment, we toss a coin and we get a value for a bit B. And then each tested oracle will output the real session key if B is equal to 1. Otherwise, it will output a random key if B is equal to 0. So the final goal of the adversary is to guess the right value of B. The key exchange can be broken in 3 different ways. By breaking the key exchange experiment, which is the case in which the adversary guesses the correct value of B. We can break the uniqueness of 2 partner oracles, or it can break the soundness of the scheme by tricking 2 partner oracles into computing 2 different session keys. The next step is to define a security reduction. So we have to take an allegedly hard problem and we have to build a solver to this problem starting from an adversary against our protocol. We decided to focus on the strong C-side problem, which goes as follows. In a C-side setting, we take A and B, 2 fractional ideals in 2 different ideal classes, and the corresponding elliptic curves EA and EB. A decisional oracle would output 1 when it's queried on a valid C-side triplet, so whenever it's queried on EX, EY, EXY, and 0 otherwise. But we don't give the adversary A access to this oracle, but to a more limited one. So we fix the first input of the decisional oracle, and this new limited oracle will output 1 whenever it's queried on EY, EZ, where EZ is isomorphic to EXY. Then our assumption is that the advantage of the adversary in solving the computational challenge provided access to the limited decisional oracle is negligible. A crucial property of the strong C-side problem, which follows directly from the same property of the computational C-side problem, is random self-reducibility. According to the very general definition, a problem F is random self-reducible if a solution at any given instance X can be reduced efficiently to the solution of the same problem at 1 or more random instances. In doing so, 2 conditions have to be satisfied. The random instances have to be generated non-adaptively, and they have to be uniformly distributed. Now, as we said, C-side problems are random self-reducible, and this is why we decided to go for the C-side scheme over the SITH scheme, because random self-reducibility for SITH-based problems seems to be much harder to prove. In this slide, you can see side by side the random self-reducibility graphs for the computational Diffie-Hellman problem and the computational C-side problem. So, as you can see, they are perfectly analogous. The structure of the proof is the same. Of course, the operations are different, but the structure of the proof is exactly the same. Before venturing into the security reduction, we need to define 5 different oracle types, according to their role, the partner's honesty, and agreement on the CTXT, which consists of the partner's identities, the long-term public keys, and the ephemeral public keys. Type 1 and Type 3 oracles are initiator and responder oracles who have talked to an honest partner throughout the whole session. So they have agreed on a shared secret key, and they have agreed on the CTXT. Type 2 oracles are oracles who believe they are talking to honest responder oracles, but they are not sure yet because they haven't received any response. And analogously, Type 4 oracles are responder oracles that have received a message from an honest initiator, but they are not sure that the initiator will still be honest by the time it will have received the response. And type 5 oracles are simply initiator and responders who are talking to a corrupted partner. Alright, so we can finally have a look at the security reduction. There are 6 different games, and I will give a very quick overview of all of them. Game 0 is a usual authenticated key exchange game. So, winning game 0 means that the adversary has broken the key exchange, and so it has correctly guessed the initial bit B. In game 1, the adversary has broken the uniqueness of the CTXT, and this can occur with a probability which is upper bounded by mu k square over n, where mu is the number of participants in the protocol, k is the maximum number of sessions per participant, and n is the size of the ideal class group. In game 2, we change how each oracle computes the session key. So before computing a key, the oracle checks if the adversary has queried the hash oracle, which is the key derivation function, on that input. If so, it stores that hash value, and otherwise it stores a random key. And we can see that this is where the problems start if we try to carry our proof from the random oracle model to the quantum random oracle model, because the input we are looking for might be hidden in superposition by the adversary. So we believe that with a careful use of the quantum random oracle, this shouldn't be a problem and the security proof should carry on, but we leave this for further research. In game 3, we modify how a type 4 oracle, which is a responder oracle that is unsure of the partner's identity, computes the session key. In particular, it picks a random key and then it waits until the adversary possibly corrupts its partner. If so, it then modifies the key derivation oracle with a random key. In this game, we build B1, which is the first solver for a computational challenge, and we do it in this way. Given the computational challenge ES-ET, we set the long-term public key of a random party PA to yes, while we re-randomize ET and embed it in the ephemeral public key of a random type 4 oracle. As a result, we get the following bound, in which we introduce the first tightness loss, which is due to the fact that we have to guess the right oracle. So uncertainty introduces the tightness loss. In game 4, a type 3 oracle, which is a responder oracle who is sure about the honesty of the initiator oracle, chooses a session key at random without modifying the key derivation oracle. This time we re-randomize both parts of the computational challenge and we embed them in the ephemeral public keys of type 1 and type 2 initiator oracles and type 3 oracles respectively. Note that this time we don't introduce any tightness loss, since we don't have to deal with any kind of uncertainty. In game 5, which is the last of our games, we deal with an initiator oracle that is unsure of its partner's honesty. So it's clear that this game is the complementary of game 3, in which we had a responder oracle which was in this same position. So, as it happened before, we embed the computational challenge in an analogous way, and again we introduce a linear tightness loss. In summary, we play all 6 games together in order to get to the final result. So, given that the probability of breaking the uniqueness of partner oracles is upper bounded by mu k square over n, where mu is the maximum number of participants in the network, k is the maximum number of sessions per participant, and n is the size of the ideal class group, given that the soundness cannot be broken due to the perfect correctness of the scheme, and given the three solvers we have just defined, then we get the adversary A against our protocol wins with probability which is smaller or equal to the quantity here below. So we have the three advantages that come from games 3, 4, and 5, and the upper bound on the probability of breaking the uniqueness of the partner oracles. And for simple reductions such as ours, in which the adversary is run only once and we don't use, for example, the forking lemma, the linear tightness loss is optimal. In the paper, we also provide a quick comparison between our scheme and some of the latest key exchange protocols, by having a look at the number of cycles required to run a key exchange session. We mainly refer to the two SciAche protocols that were introduced last year at AsiaCrypt. And as we can see, our scheme is at least one order of magnitude more efficient than the SciAche schemes. So in summary, what we've done in this paper is building a post-quantum key exchange protocol with optimal tightness, without compromising efficiency or key size. The protocol itself is an easy adaptation of Protocol Pi by Kock, Gordon, and others, but adapting the security proof was not so straightforward, because, for example, we only had one operation to play with instead of two operations with the exponents in the usual Diffie-Hellman setting, and we require random self-reducibility of the computational C-size problem. For future work, we have seen that our protocol is secure in the random oracle model, but I pointed out in Game 2 that this security proof might not carry on in the quantum random oracle. So is it possible to do so or not? Then the security against ephemeral key reveals usually increases the tightness loss. Is then possible to move to a stronger security model in which we allow this type of queries without losing tightness? And the last open question is if it's possible to adapt this same protocol Pi to other post-quantum settings. So, this is all for this talk. Thank you very much for your attention, and please feel free to get in touch with me if you have any questions.